Lecture 7, Aspects of the Celestial Sphere. In this lecture, we're going to talk about stars, why we see them at different times, how we can actually monitor them, and it's really cool because we're going to use this a lot, this whole unit, and we're going to do some activities on this in class, which I hope will be fun for you all. But the big question is, why do we see stars at different times? Stars move very quickly in their own orbits, but we don't see it that way. To us, they kind of stand still. And this is because they are so far away, it takes about 50,000 years before their change actually reaches us. Our sun is also moving. It moves through the stars on a path called the ecliptic, which causes different star patterns to be seen, which we know as the zodiac. This all has to do with the sun moving on its ecliptic, Earth's rotation, so the time of day, Earth's orbit around the sun, so the time of year, and your location on Earth. We see different stars in the northern hemisphere than you do in the southern hemisphere. If you ever, for some reason, go on a vacation where you go to South America or Africa, when you look up into the sky, you will see different stars than you would here in Florida. Sailors were able to use this to figure out where in the world they were, what time of year it was. People have used the stars as guides to where they're going, what time of year it is, the type of season that's happening for hundreds and hundreds of years. One could even say thousands of years. At night, when you look up, you will see stars which appear within a huge dome that ends at the horizon. It looks like a dome, but the stars are actually at varying distance. Our closest star, other than the sun, is actually 4 light years away. Even the planets of our solar system, which are super close compared to 4 light years, are difficult for us to get a real sense of in their 3D arrangement without specified measurements and calculations. But for studying stars with the naked eye, it's much easier to pretend that the stars are all in fact the same distance from us. That dome that I mentioned before represents only about half of the sky. The other half is below your feet. And because it seems like a dome, you're actually able to map how long it will take for a star to rise or set. And this is called the celestial sphere. It is a 2D map to show stars. It is always Earth-centered, because from our viewpoint, we are the center of this dome. Stars surround the Earth in all directions, forming a starscape on the celestial sphere. We actually use this to try to map stars, where they're going, where they are in the night sky at what time. It's actually a pretty cool, nifty object that we use. Just like on a map or a globe, there are 2 directions that pinpoint each star, or 2 numbers, like latitude and longitude. But in this case, latitude is our parallels, and longitude are the meridians. Earth is a sphere, and a sphere is 360-degree circle, right? We use degrees,
minutes, and seconds
as our measurements. 1 degree
is 60 minutes, which is 3,600 seconds.
The north and south poles are fixed reference points, and the equator is the imaginary line around the center of the Earth, splitting it into the northern and southern hemisphere. And then we have the prime meridian, which is an artificial 0 degree, which passes through Greenwich, England, and it creates the imaginary line that splits the Earth into the east and west hemispheres. Parallels are imaginary circles drawn parallel to the equator, and meridians are the half circles from pole to pole that intersect parallels at right angles. Just want to point out, the prime meridian is the equator of meridians. It's arbitrarily chosen as an artificial 0 degree. It's not Merlin's successor in the Sorcerer's Apprentice. That is the prime meridian. Latitude is the angle measured from the equator to the desired plane, either north or south, relative to the equator. Okay, this is always relative to the equator. So if this is our equator, if you are this way, you are now going north. If you are this way, you are now going south. It is the same latitude on any single parallel. If you're over here, you're still, let's say 5 north. If you're over here, you're still 5 north. If you're over here, you're still 5 north. Longitude is the up-down version. It's the angle measured in the plane of the equator from the prime meridian. It is either east or west relative to the prime meridian. It is the same as long as you are on any single parallel. Prime meridian. If you go this way, you're going east. If you go this way, you're going west. No matter where you are on it, it will still be the same. So this is 0. It will still be 0, 0, 0. When we intersect the equator, you will be 0, 0 here, 0, let's say 10 south here, and let's say 10 again, 0, 10 north there. And this is how the coordinates work on Earth. We have the North Pole, the South Pole, we have parallels, we have the equator, the latitude for north and south, meridians, the prime meridian, and longitude east-west. On the celestial sphere, these actually translate. So the North Pole becomes the North Celestial Pole. The South Pole becomes the South Celestial Pole. Parallels become declination circles. The equator is now the celestial equator. Latitude, north-south, becomes declination, positive, negative. Same thing. It goes above and below the celestial equator. Meridians become hour circles, and the prime meridian becomes the 0-hour circle. And then we have longitude. Longitude becomes right ascension, or RA. Okay, it goes from 0 to 24 hours. It does not go 0, 24 one way. It is completely around in a circle from 0 to 24. If you need to look at this again, look at it with all the arrows. Really helpful. Angular measurements of the celestial sphere. It is still a 360-degree circle. The celestial sphere is a 24-hour circle. So instead of degrees, we use hours, minutes, seconds. Okay? A 1 circle is 24 hours. 1 hour is 60 minutes. 1 minute is 60 seconds. Right ascension, RA, or alpha, is the celestial longitude. Declination, also given as dec or gamma, is the celestial latitude. Okay, you need to know both of these sets of symbols because it can show up either way, on a lab, on the in-class activity, or on your exam. Constellations are a loose grouping of visible stars. Basically, we have all these stars in the sky. Someone looked at them and said, hey, these guys are close together. Let's give it a name. Basically, ancient astronomers looked at the night sky and said, that kind of looks like Leo the lion. And so they named them. Hydra, Sextant, Virgo, Leo, Cancer, Leo Minor, Canis Venatici. Most of these were created by the ancient Greek astronomers. For example, Ursa Major and Ursa Minor, the large and small bear, Canis Major, Canis Minor, the hunting hounds and companions of Orion. The International Astronomical Union recognizes 88 official constellations. 88. And there are quite a few unofficial constellations. About half of the 88 have ancient roots, particularly the large ones. The rest of the smaller ones are mostly recently made by cartographers while mapping the night sky. The unofficial constellations in common use are known as asterisms, such as the Big and Little Dipper. The Big Dipper is part of Ursa Major. Generally, constellations are connected with legends to others like Canis Major and Minor to Orion. Some constellations were named by European explorers as they sailed to the southern hemisphere, like Telescopium, Microscopium, which is telescope and microscope, and one of my favorite is Antlia, which is air pump, and Sextans. Most constellations, though named by ancient Greeks, but most of the stars are from Arabic words. Ancient Greeks may have named the constellations, but the Arabs named the stars. For example, Betelgeuse, and the second brightest star in the Leo constellation is Denebola, or lion's tail. So we have changes in the sky. Remember, different times on Earth depend on what star pattern you'll see. Even 10 minutes, our time, will make a difference thanks to Earth's rotation. Different dates, too, even if at the same time, will lead to different star patterns because of our orbit around the sun. So remember, the sun is in a different part of the sky every day. It's in a different place in its own orbit every day. So based on the sun's orbit, our orbit, and our rotation, we will see different stars. So we have different points of view. We have star-centered, where Earth rotates counterclockwise and one rotation is a day. And then you have Earth-centered, where we get the celestial sphere, which is rotating and you are still instead. Stars appear to rotate clockwise from our point of view when looking at the northern celestial pole. It seems to be rotating from east to west. It's the same amount of time to rotate as the Earth day. It's very important. One rotation on the celestial sphere is equal to 1 Earth day. Part of the sky located directly above the North Pole is known as the North Celestial Pole. They're essentially identical, just on the celestial sphere. The star Polaris, which currently is our North Star, lies close to the North Celestial Pole. The pole is a fixed point on the sky, so the closer you get to this pole, the less the stars appear to rotate. If you are directly on the pole, the star will not rotate. It will not move from our perspective. Kind of like when you have clay and it's centered on the spinner, it won't look lopsided, but if it's not centered on the spinner, it looks lopsided as it's spinning. Same thing. When something is centered directly in the center of the spinning object, it appears to not move, versus objects on the outside appearing to move. We rotate around the sun west to east, from a sun-centered point of view. The Earth moves 1 revolution in a year. But from Earth center, the sun travels around us in 1 year. Basically, we have the same rotation, which is kind of nice. Makes things easy. The path the sun travels among the stars, that's called the ecliptic. So as the sun moves along its path, it will pass 12 zodiac constellations. Technically 13, but we're only going to use 12 because that's what is recognized. Earth's axial tilt is 23.5 degrees. The ecliptic and celestial equator interact at 2 specific points, and this is the 0-hour circle. When they interact at the 0-hour circle, you have the vernal equinox, which is spring, and when it comes in contact with the 12-hour circle, it is the autumnal equinox, also fall or autumn. And these are very important. Every year, the equinox or solstice dates and times actually get adjusted based on when it reaches the 0-hour circle. If the vernal equinox, or the first day of spring, happens on March 20th, that means every other solstice or equinox will happen on the 20th. If it happens on the 23rd, same thing. So basically what it looks like is we have the celestial sphere and we have Earth, right? Earth is tilted, we have the celestial sphere, which is perfect, right? Celestial sphere. Whee! Basically, as it's turning, the equator and the 0-hour circle will interact here. And then again on the other side, which is the 12-hour circle. When they interact is when you have the first day of spring versus the first day of fall. So spring starts somewhere between the 20th and the 23rd. It is most commonly occurring on the 21st. And in many ancient beliefs, like with the Celts, solstices were considered holidays. And so in people who still celebrate Wicca, for example, these holidays are very important, and they will celebrate them every year. You'll have the first day of spring and the first day of fall. What makes these guys so unique is that you have an equal amount of day and night. Day and night are equal. For the summer solstice, you have the longest day of the year. And for the winter solstice, you have the shortest day of the year. And it kind of looks like this. So let me erase everything really quick. Here's how it looks to us. We have the spring equinox happening here in March. The equator is touching on the 0-hour. For the June solstice, it's not touching an hour circle necessarily. It's more touching down here. September, we're touching on the 12-hour. And December, we're touching again down here. What is this 0-hour circle? It is the intersection between the celestial equator and the ecliptic. It is the vernal equinox. Autumnal equinox, 12-hour. Vernal equinox, 0-hour. Winter solstice, 18-hour.
Summer solstice,
6-hour. So right here we have the 0-hour circle. This is the 12-hour circle. Because you go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then again, 18. Okay, this is the 18-hour. Right? So these all have to do with these lines right here, the meridians. This is all a 24-hour clock, essentially. So when you have an intersection between the celestial equator and the ecliptic, it is known as the vernal equinox or the 0-hour circle. Fun fact time. Zodiac stems from the ancient Greek word for animals. The sun actually passes 13 constellations, and as of the year 2000, if you were born in the first half of December between Scorpio and Sagittarius, you are actually considered of the Ophiuchus, or the serpent holder zodiac sign. So why wasn't Ophiuchus part of the original zodiac? Well, scientists think it was because ancient astronomers weren't too sure about the sun's path, and there was some vagueness on constellation boundaries. Some zodiac names are actually due to seasons. Example, the sun's appearance with Aquarius meant rainy weather in the winter of Europe, which it is. During our winter, the Earth is closest to the sun in its orbit at its perihelion. Well, let's move on to some horizon coordinates. Remember, Earth coordinates, North Pole. On the celestial becomes the North Celestial Pole. So now we're moving from the celestial sphere to literally this, where you are standing right here. In this case, you're going to have a whole bunch of things. The North Celestial Pole becomes the zenith, which is right above your head. The South Celestial Pole is going to become the nadir, which is below your feet. The celestial equator is the horizon. You will never reach it. No matter how hard you try, you can never reach the horizon. Declination circles become altitude circles, essentially how high off the ground and how close to the zenith you are. Declination becomes altitude. The 0-hour circle becomes the north point, which is over here. Hour circles become vertical circles, and right ascension becomes azimuth. Is it to the right or the left of the zenith? Now let's take a look at this. Zenith, literally the point over your head. If you were to look directly above your head, and I hope you do that right now, that is your zenith. If you were to draw where you were, that would be your zenith. Over here, this black line down here that your imaginary stick figure is standing on is the horizon. The actual dome is the celestial meridian. The horizon is the center limit of view. It is the middle, the ground view. Basically, when you're standing at the ocean, the line that you see curving is the horizon. It is a line along the edge, and you will never, ever, ever be able to reach it. It's also where the sun sets. Now let's talk about altitude. The angle from the horizon to the sky is known as altitude. It is always between 0 degrees and 90 degrees. If it is greater than 90 degrees, you are probably facing the wrong way. So remember how I said, depending on if you're to the right or to the left of the zenith? Well, when you're in that lovely little dome, it is always between 0 and 90 degrees. It makes a right angle. Depending if you're over here versus over here. It's not like it's going to go, oh, almost 180 degrees. It's going to go, oh, maybe over here is like 10 degrees. And over here is like, I don't know, 45 degrees. Do you see what I'm saying? Azimuth means direction. This is essentially what you need to remember. Azimuth means direction. If it has as in it, it's telling you the direction you should go. North, south, east, west, and in between. We talk about these in the degree form, 0 to 360. North is 0, east is 90, south is 180, and west is 270. These are numbers you should remember. You will also need them for the lab. Now let's talk about azimuth and altitude. Let's figure out the azimuth and altitude for numbers 1 to 9. All right. So, if we're going to make this a little bit easier for you, we're going to draw it like this. Here is the north, the south, the eastern side, and the western side. This is essentially what we're doing. If your spot falls anywhere on this circle, or in this case, the line, which is the horizon, it is equal to 0 for altitude. So, for numbers 1, 3, 4, 6, 7, and 9, your altitude equals 0. But 1 falls on this side, and 3 falls on this side. 4 and 6. 7 and 9. So that means our azimuth is going to be the following. Number 1, altitude, azimuth. Okay, altitude, 0. Azimuth, east. East is 90 degrees, but we are essentially east, so 90 degrees for now. Number 2, we'll get to. Number 3, again, altitude is 0. Now it's on the western point. West is what? We have 0, 90, 180, 270, right? So in this case, 3 is 270. So now let's do number 2. If it falls on the meridian, it is either going to be north or south. There will be no east or west, no in between, just north or south. In the future, this will be southeast and this will be southwest. So in your lab, you will have to mathematically find southeast and southwest. And it's basically off by 15 degrees. So remember, north is 0, northeast 45, east 90, southeast 135, south 180, southwest 225, west 270, and northwest becomes 315. Then we go back to north is 0. To go back to number 1, if it's down here, this is southeast. Southeast is 135, so our azimuth is 135. Southwest, 225, so our azimuth is 225. But for number 2 is either north or south. There is no northeast, no southeast. It can only be north or south because it's up in the sky. It's either going to be north or south of the zenith. So number 2 is south. South is 180 degrees. Now let's look at azimuth. If this is our right angle, and up here is 90, and this is 0, about here is 45. What do you think number 2 is? So what I want you to do, as part of your assignment for this time, is going to be coming back to this slide. I'm going to post it. And you're going to have to tell me what you think the altitude is for 2, 5, and 8. And then the azimuth for 2, 5, and 8 for 6, 7, and 9. Okay? I have done half of it for you with altitude. And I have done some of the azimuth for you. I have written all these down for you. I suggest writing them down and using them to answer it.
Now let's move on to the celestial sphere. We use it to find how stars cross the sky, and to do so we're going to use declination and right ascension. To find the maximum altitude, we're going to add the celestial equator, which is 27 degrees based on where we are, to the declination. An example of this is Sirius, which has a right ascension of 6 hours and 45 minutes and a declination of -16. So to find the maximum altitude, you take the celestial equator, 27, and you add it to 16, which is a negative, so we are going to subtract it. This is going to give us 11 degrees, which, since it's not over 180 degrees, means that it is in the south of our celestial sphere, and so we would say its azimuth is then south or 180 degrees.
Okay, so what we just worked on didn't have a number greater than 90. Remember that our number right here at the zenith is 90 degrees, right? So, well, what happens if you add these two numbers together and you get more than 90? Well, that just means you have to start from the other side, meaning you just have to subtract by 180 degrees. Let's take an example. A declination of 68 degrees. Okay, we add that to 27 degrees because that's the distance between us and our celestial equator, and we get 95 degrees. Well, that's greater than 90. So what do? We take 180 and subtract it by 95, and we get 85, meaning our max altitude is 85 degrees. And since it's positive, 85 degrees is right about here. All right? And just please remember that. If it's less than 90, you are A-okay, right? Less than 90, you are perfectly fine. Greater than 90, subtract by 180. All you need to remember for this. This is how we're going to do this part of the lab. All right? And that is our class for today. I hope you enjoyed at least a smidgen of it, and I'll talk to you guys next time.